the alignment of the building was one of the key components. So at the same time, we needed to fully understand the characteristics of the material. So we had I put in place a very, very extensive testing program and concrete planning work for the entire project. So we knew everything about the building as we built it. So today, I think I'll be able to, it's like, for me, it was like an engineer's dream to be able to be involved in the design, the construction, and at the same time being able to monitor the building and get feedback, not only from a gravity, behavioral standpoint, but also to look at the dynamic characteristics of the building, both under wind and seismic events. So we have the opportunity to fully test the building, just like having a full-scale aeroelastic test on the building. So today, obviously, as most of you know, that curve or tablet cause is captured human imagination because of their scale, symbol of nature, and also because it's a financial well-being of the country or and also technology and potential being iconic representation of cities. And Burj Dubai is no different than that. In fact, it brought more fame to Dubai than anything else. Yes, we have a number of Hong Kong, but in China, one financial center in the north, including the World Trade Center, Singapore, Shanghai, and we sold just that Nishan Tower and also Lotte Tower right now. And really, from my experience, we started the Burj Khalifa in particular. As you know, this whole development that you can see here didn't really exist. So we had only just started with the Burj Khalifa. At the time, it was called Burj Dubai. But honestly, I think when we started this project, I was completely surprised in the selection of the structural system. We debated what kind of structural system we would allocate to. It's the tallest thing in the world. It's certainly supposed to be steel, but for this building, because of its use, it's more adaptable to concrete construction. But before we started that project, because of the social environment in Dubai and in the Middle East in particular, we have to be extremely careful whether what kind of concrete we select. So we were a little bit worried about that. So we spent a bit of time trying to understand the environmental conditions and the impact of selecting concrete and what kind of protection we need to do from a corrosion standpoint, sulfate, chloride attacks, and so on. So we had to have a very careful selection of the materials. So we spent a bit of time understanding that. Again, in Dubai, as you can see, there's a lot of road structures that have been proposed at the time. So I essentially gave the architect the blank check to do really whatever they wanted to do from an architectural standpoint, that you can see from some of the buildings that have been proposed. Again, we have now the Kingdom Tower. And during this time also we started looking at, almost very tall and slender building which push the engineering limit to completely different levels. Instead of the higher walls of the building become sometimes the dominant mode in terms of the construction criteria for this building. So some of these things, all these things have to be considered in the design and the planning work that we look at. And also, these big buildings definitely they do require. You don't have forever to build these buildings, so the selection of the structural system is very important role. So and also, I told you this is more about technology and also huge amount of management. As you can see, at the deep time we have about 15,000 people, more than 50 to 60 consultants to coordinate. So these very large scale development projects require huge amount of coordination and the introduction of new technology in order to be able to build them on time and successfully without any problem. Again, some of the factors that most of you know that influence the design of super tall buildings. This is no different from including financial, environmental, and also A lot of times what we can drive the architectural design, whether it's uniform architecture, creating sculpture, sustainability, and so on and so forth. And also engineering solutions currently have been the driver for building. And actually, Burj Khalifa, as you can see from the lecture, was no different than any other building that was driven by actually one engineer in particular. Again, we have to be cautious with the cost. We have to be worried about how do we shape and geometry play important role in the cost efficiency of the building, size of the floor plate, structural solution, in terms of being able to build it very fast. And without a structural design that's adaptable, construction methodology that we end up with a lot of trouble during construction, facade, transportation system, environmental strategy in terms of the life cycle constraints, and some of the market conditions that we have to look at is the history of it. Who is better? And these are the kind of things in terms of risk that we have to take into consideration during design and construction. So I think what we have seen was buildings have to be rational, fast to build, sustainable, elegant, and also contextual. The other issue is also sustainability. We talked a lot about. As you can see, the cities tend to be better than others. Obviously, this is not the talk, and also, having, especially in a harsh environment, we cannot keep spreading the city, as you can see from some of the pictures we sold and Japan. So, if we were to look at consolidating, especially in the desert environment, from the environmental standpoint, the more the denser the city is, the more efficient it becomes. And its demand on infrastructure is much better. But one of the things that, for me, that drives sustainability is the embodied energy in the building. For example, if we were to build Burj Khalifa or any sort of tall building, the floor framing, the architectural or the facade or the mechanical system for the floor does not necessarily cost more than what you have in the typical floor. However, the structure, because of the stacking effect, tends to be extremely critical. Obviously, the elevator is more expensive. But at the same time, you look at the embodied energy you have from structural standpoint. This is, by the way, from the concept of building an urban habitat. It can play the major role. So the question is, with the limited amount of material that we have to put in the building, such as the Burj Khalifa, how do we make design an optimal design without them adding any more than what I need for gravity loads? So structural system efficiency plays an important role, and gravity load management plays an important role. For example, building our target, we didn't want to take this, as you can see. I don't know if you can see the arrow. You get the floor framing, you get the column stacking impact, the stacking of the building, the floors, and then you have the impact of the wind and seismic impact. So our target is from this project is from the very beginning not to exceed what is needed for gravity in order to optimize the amount of material that we need in this house. So that's for this reason, managing the gravity load system plays a very important role. So fundamentally, you can look at Burj Khalifa, and you may think of it as being John, can you see everything, or is there a problem?
Yeah, we can see your slides, and we also see the pointer.
Okay. Because I get the message, I was a little bit worried. So at this moment, so what you can see, I think fundamentally, Eiffel Tower to me is one of the most efficient building systems in terms of managing the gravity load. So fundamentally, it's a concrete building. As you can see, the structural system is an all concrete building, but the way we manage the load, we're able to drive the highest gravity load to the extremities of the building in order to maximize the moment of inertia per se, or the distance, and also actually to keep the building under gravity load. So essentially, we didn't, in this building, manage the gravity load in such a way that we did not actually change, in which we didn't allow any of the elements to be subjected to tension, which means that we had the minimal amount of rebar in the school. So in order to talk about just to briefly talk about the structural system, some of the key issues that we looked at is regarding load management. We have Seismic Engineering Management, which played a major role from the very beginning. We know the building engineering will drive the design, so what we had to do is organize the building structure in such a way that we reduce the cross-building response and the vortex shedding correlation along the entire height of the building, in which we reduce the impact of the cross-building response on the building and reduce the load forces significantly. And also equally important, reduce the acceleration of the building. And also selection of the structural system that is adaptable to the construction method to expedite the construction without any hiccup. So these are some of the strategies that initially considered. Now, Burj Khalifa obviously is a very large-scale development project, about 1 million square feet. The total cost of the total development is about $20 million, and it was due to be completed in 2008. Consists of the residence, business park, the old town, the Dubai Mall, and the center of the entire thing, which is Burj Khalifa center here. So the project is Burj Khalifa, 160 floors, consists of 828-meter tall building. It's about 480,000 square meter, which is the architect and engineers is S1. PM, project manager, planner, the contractor is Samsung V6 and Architect. Consists of about mostly initially also the use of the building really is initially it was a residential tower, then during the life and during the design of it changed into multi-use, into residential, into hotels, into service apartments, into boutique office, and at the top of the building we have communication and also some mechanical plants at the top of the building. Again, it's a multi-use, so that complicated the project. So this is here the complete of the project. This is the complete of the building during the night of the soil in the morning. Here, what we have essentially, where did the concept come from? As I mentioned initially, you can see it's beautiful. It has an Islamic architectural component to it, what really initially started with this building, which is Tower 3 in Korea, essentially consisted of the tripod shape. During the design of this building, and we did the internal testing program, we discovered that the spectral density in this building was excellent, which it was not that sensitive to the external to the directionality of the wind. And we didn't have, the building was extremely quiet, so we didn't have much resonance because of this. So we used this concept, as you can see, variation of the shape and also the changes of the shape of the building around that glass we designed. And it was done all residential, so we didn't want to have every window, every room also almost when the building has to have an access to the natural light. So what you see here essentially is the Tower 3 building in Korea that we did. Later Smith, by the way, S1 Design was the designer also. And this is Burj Khalifa. As you can see, it's, if I were to superimpose it, the Tower 3 is just it's about 200 meters, about 300 meter tall tower, which was reduced in the time to about 273 meters. But the window is the same, which essentially it's like modular kind of construction from design standpoint. So obviously some of the early integration of architectural and structural concepts were extremely critical, estimating the relative floor area with engineering, estimating the effective depths and the natural light of the building, especially for an old residential building. And structural system continuity without any concern, the modulation of the system is extremely important. And also the construction method was one of the key components. So the structural system that is only design strategy that made from structural standpoint. The structural system selection has to be continuous throughout the complete site. Utilize latest technological advances in structural material while utilizing the local labor and skilled labor and construction available at the time. And also manage the gravity load to maximize its resistance to wind effects, and also the effective minimizing the amount of material to be used in the building. Optimize the structural system from stiffness, strength, and redundancy in construction. And one of the things that we did a special, by the way, for this building is from EARTHQUKE is to test the concrete and specify the performance stage concrete that has limits, which we tested before we actually specified it. And also use the building extremities to maximize the effective depth of the building and to prevent any uplift or tension even under extreme loading conditions on the tower. And also we have to improve dynamic characteristics of the building under wind loading by tuning the dynamic characteristics of the building to improve its dynamic behavior and to prevent loss of vibration. This was fundamentally part of the design, and also enhance inherent building dynamic characteristics to achieve dynamic behavior response without additional dynamic devices, and also selecting an incumbent system that has a means of effective energy dissipation by carefully defining the zones of the structural choices that dissipate energy, and also the control the relative displacement, also essentially between the building by equalizing the stress level between the elements to control their behavior. So yes, this is a summary what I just talked about from a gravity load management standpoint. What you see here is the building that essentially consists of a central core here and 9-meter modules. And each of the modules I would define them like bricks. Almost each one of these columns, essentially they never ever size. So all the columns stay the same dimension. So as the building, if you were to think of the column, or the building as one column, essentially all you needed to do with time is just add more construction to the building. So the column, none of the wall thickness change their size from bottom to top. But we were able to reduce the stress. As you can see here, this line here is, yeah?
This is great. Just quickly, just a time check. We're about like 20 minutes in, so about 10 minutes left, just to make sure you're getting to the key.
Okay.
Points you want to make.
I'll switch. But what you see here, essentially what we have is the gravity, the amount of material that we need for the building, for gravity load, and this is what we have in the end. So essentially, that's our target in terms of minimizing the amount of concrete that we need. Obviously, we have wind engineering studies that we have done. I'm not going to spend a lot of time on that, so pretty much the summary, what you will see here is this is a CFD model that we have done, and you can see this is the building frequency and the frequency, vortex shedding frequency with the different wind velocities is completely uncorrelated. So essentially we eliminated the resonance conditions that come the design of the building. So we did the one tunnel test, including inelastic, without talking a lot about the engineering, inelastic test, also looking at the calculations because they are accessible to look at the velocity, driving pressure, and the acceleration of the building for 1 year, 5 year, 10 year, were within the ISO standards. Essentially, we need to verify that the structural concept we selected was optimum and so on and so forth. Stack effect, another thing we needed to consider. Seismicity. I'm just bringing these issues, by the way, just to We will look also at the seismic, and as you know, this is Iran is a very active area, and the bias is over here. So far, in fact, as far as we have EARTHQUKE plane division wall from South Business standpoint. So we did have non-site specific analysis of those zones. So you guys know a lot about this, so I'm not spending too much time on this. But this is a very, very active seismic area on the bodies over here. So we have to be aware of visual levels. So this building, as most of you know, is not that sensitive. It's more controlled by wind than really seismic issues. So, but anyway, so the structural system essentially is concrete up to 156 floors, and it's just a steel to the Spire, which is more than 208 meters. Again, for the minimal amount of concrete. Now, the whole structural system is essentially actually in a single column. Probably one of the simplest buildings in design. You have this floor being the same. The visual forces come along these two walls into this canals where we kept the maximum gravity load and including the mega column, and all the stress level in these elements remain the same. So what you will see here is calculating the moment of inertia over the fact that the building is very simple. Almost every one legal movement area. And also we connected every 27 floor, all the columns together to equalize the stresses cleanly. So the building deflection is within H of 500, that's still no issues. Now where some of the key issues that we looked at is the health monitoring program, in which we needed to measure strains, column shortening, measure the climate conditions in terms of the wind, and also measuring the lateral displacement in the building using GPS, and also measure survey, and also the overall GPS system for the building, which we had the rover and also the station here. So this is just a picture to demonstrate that we have instrumented almost every column, most of the column in the building, including the core wall, to measure the strain measurement, and also to evaluate column shifting in the building. So this is a very much more instrumented, and we have the data really fit time on the building behavior. This is a typical example, as you can see, showing the speed of vibration on the column, and then also the strain measurement and distribution between the rebar and the structure steel for an element. And it's all essentially we were getting this information from real time. It's just a picture of all the instrumentation for each of the building. We measure the actual load distribution to make sure that it's consistent with our design assumption. We also did a very detailed construction sequence analysis that included heat and shrinkage effects. Some of these chunks would take about 6 days to run, and part of it is to correlate what actually happened in the building to what we are measuring in real time and make modifications and to measure photograph from a lateral displacement of the building. We also looked at the sediment and the column shortening in the building, which is essentially being very consistent to what we have done. But also we use the GPS and the local survey in real time and look at the drift and the movement of the building with time in order to correct it to its verticality. So as you can see from this chart, this was what we predicted, the solid line and the one with the dot that we measured. Essentially, there was a perfect correlation between what we had measured and what we extrapolated. And this is also the time. As you can see, sometimes we had to ask them to speed up the construction. I had to ask them to speed up the construction in some area in order to get the element stabilized, in order to get the respect. And again, we used the GPS system to do most of the survey and also the displacement of the building. We used tilt meter to get the view time, evaluation of the under tilt good time in order to keep also this alignment, which is also can be used to calculate. So some of the issues that we looked at is also installation of, we installed a house monitoring program to calculate the displacement, acceleration, and the seismic response of the building. So what we have is installed all sensors along every 27 floors, and all of it is essentially collected at the base of the building in a single data center and emitted in real time to myself and to the University of Notre Dame. They worked with me very closely on this one during construction, and later on we may as well CPP work with us in additional instrumentation for the building. So the whole idea is to monitor building movement, acceleration, displacement, weather, speed, direction, temperature, humidity, and also from there, from measure data, we look at what shape, stamping, behavior of the chemical, especially against fatigue, looking at the work profile, and also looking at the prices to make sure that we get enough pressure, to make sure they are safe and they trigger when we can open, close the windows. So what we have is we have also these solar meters along the three wings and at the center of the building along the height. So as you can see during construction, we also wanted to ensure that we have a full understanding of the behavior. There was a big earthquake in Iran, so we were able to actually measure both the acceleration and also the transistor record at the base of the building and correlate that to what we have measured. So this is in August 4th. There was another earthquake in Iran, part earthquake in which we measured the acceleration and the building movement along all levels, and also we looked at the control, all the building frequencies, and from the top of the building, surprisingly, we were able to pick up to about 20 or more, even more, if you want, in one shapes of it. So essentially, we have a full elastic elastic. And this is what you see from our screen. Every 1/10 of a second, we know what the building is doing, it's fine. So we have the wind, we have the seismic, we have the building movement measured. And also we monitored the wind, essentially at the terraces. As you can see, we have complete measurement of the wind speed at every level along the height of the building, and that information we have it in the community. There was one big event that happened, as I mentioned, in July 2010, a big earthquake that happened in Iran, magnitude of about 7.8. And this is here where the location of the epicenter of the earthquake, and this is here where Burj Khalifa was. So we were able to, this is the information we got. But we also have many records. So from there, just because of shortest time, we were able to measure the acceleration of the building in detail, and we were able to take the transistor record that we get at the case, and we analyzed the building. But by the way, for new information, we measured dynamic properties in the building. What we measured versus what we calculated was within 2%. And surprisingly, when I also compared SLM analysis to hydro analysis, to all analysis, what we discovered, only technique doesn't play a role in terms of how close you are to the real ones. So that's another matter. But what we measured and we predicted, essentially, as you can see from here, we're not too bad. So the other one is related to what is really the landscape of the building, which is another subject, another that we didn't discuss. And during construction and after completion, these just some of the building displacements predicted versus what we measured actually wasn't calculated. In the measurement, unfortunately, during this surface in particular, the GPS didn't perform as well as we expected, but we were able to, when we practiced the record, to calculate the actual displacement of the building, which was not a whole lot, but not the physical doesn't a lot actually. So this one here, we have about, during this project, was about 80 million a year, with all the political, either way. And the building did not move much actually during this program. And surprisingly, also the building in the region had been shaken, but this one it really did not move much. So, this one here is just a comparison between what we measured versus what we predicted. This is really the building dynamic properties of the frequencies. So x-axis and y-axis, and so we were able to correlate, as you mentioned, we were within 2% from each other.
We're close to finishing up the time, so I wonder if do you want to jump to some concluding comments?
Yeah. So what I wanted to say, I think this building essentially it was really, it's one of the, even though it was one of the most important building. It's the tallest building structure ever built, but for me it was one of the simplest ones actually to design and also construct. From a design standpoint, it acted like a single column and a single cantilever. And also what we have is what we designed versus what we constructed versus what we measured almost, I would say, that it was as you will ever get. And for me, I was extremely fortunate to be able to be involved in this building and in all aspects of the design and the construction of it. And I think this is the building in particular have gave the concrete, 100 years ago, nobody would ever have a dream to build a super tall building with concrete. And because of the concrete technology that we have today, there is nothing we can do to scale that we cannot do with concrete in terms of that construction cycle. Now, in terms of building monitoring program, I think, in my opinion, this should be mandatory for all building systems, visual building systems. And there's so much, I think, we can learn. We spend so much money in the testing program, and yet I think building authorities should be able to reinforce installation of monitoring program into these important buildings to give us a feedback in terms of the actual behavior of these buildings, and in order to be able to feedback to the research communities to be able to modify all improvement standards to reflect what we are really measuring. And we are really missing this opportunity from my building. For me, for every building we are building right now, is becoming part of our standard practice. And so almost the amount of measurement that we're getting right now is very, very important, I think, to us. And I hope in the future I can write more to share some of this data with everybody in our professional community. Thank you very much for your time, and I do apologize for being remote. If there is any questions you have, please feel free to contact me at my email. And if you have any questions, please let me know.
Okay, well, thank you very much. Really remarkable project. We'll have to, when you're passing through San Francisco, get the full version. I think our students, I know there's some students who are real curious about damping values. But, and I know, Ahmad, you're up early there. You got to get on to your busy day. We have kind of the next speaker we got to move on to here. But again, I'd like to kind of really thank you for joining us today. Okay.
Yeah. Well, thank you very much. And I'm sorry again spend more time on listening to everybody, sharing what we're thinking and state of the art. And Mark, thank you very much for inviting me to this lecture. I very much appreciate it. Hope to see.
Yeah, okay, we just saw the fireworks display. Okay.
Thank you very much.
Thank you. Yeah.